Welcome to the course of Advanced Classical Mechanics. My name is Mikhail Frolov, and today we're going to discuss Lagrange equation of first type. So, as you know, the dynamics of all mechanical systems can be described in terms of second law of Newton here. So, P is a momentum and P is a product of mass and velocity. So, in a second law of Newton, so F is well-defined force which acts on our system. So in order to find uniquely the law of motion, so we have to formulate initial condition. So we have to know position of our system at time t equals 0, and we should know the velocity of our system at time t equals 0. So how we can change that formulation if we have a constraint? So if you look on that example, so we have some constraint, and along of this red line, some particle can move. And on that particle, we have an action of our gravity force. But instead of vertical motion, our particle will move along of that line. So why it moves along of that line? So because here we have additional force, so-called constraint force. So because we have a constraint here, y equals f of x, so we have additional force which cannot move or cannot allow to move our particle vertically. So how we can define R here, or constraint force? So in general, our force can be divided in two parts. So active force, which is well defined, Fa, and constraint force, which we have to define. So in order to define constraint force, so we have to introduce virtual displacement. So what is a virtual displacement? So virtual displacement is a displacement which is allowed by our constraint. So how we can define constraint force? So let's consider so-called perfect constraint forces. So what is a perfect? So we consider such a forces was action on the virtual displacement is equal 0. Means that constraint forces is perpendicular to the virtual displacement. In that case, we understand that virtual constraint forces should be perpendicular to our surface or to our function f of x. So R should be defined as a gradient of function of f. So in order to introduce the length of this force, so Lagrange had introduced so-called Lagrangian multiplier. So in general, our force in total is the sum of active force and constraint force, which is a multiplication of Lagrange multiplier and gradient of function of f. So if we have some constraint here, so our second law of Newton, or Lagrange equation of first kind, can be presented in the form. So changing of momentum is given by active force and constraint force, which we define right here. So in order to define uniquely law of motion, so we have to define initial condition as in a second law of Newton, which we discussed before. So lambda here has to be defined. So, but we can define. Why? So because we have the same number of equations and the same number of variables which have to be defined. So let's formulate in general our problem. So we have n particles. So n particles can be characterized by 3n dynamic variables or 3n Cartesian coordinates. So we know all active forces which act on our system, and we have a k constraint. In general, we consider the case only holonomic constraints. So problem. So how we can define constraint forces and how we can find law of motion of our 3n particle systems. So in general, so we have to apply second law of Newton, and Pi here is a momentum of ith particle in our system. Fi is a force which acts on a I particle, and Ri is a constraint force which acts on the ith particle. So in general, we have a k constraint here. So and position of our system we will be described in terms of new variables. So we have a set of variables R1, R2, and Rn, and we consider new set of variables x1, x2, x3, up to 3x, 3n. So let's say if we wanted to consider x4, x4 is just x projection of vector R2. So from that set of variable, we have a k variables, so-called dependent variables, and we have 3n minus k independent variables. So how many constraints we can hold here? So we have three possibilities here: k equals 3n, k larger than 3n, and k less than 3n. So if k is equal to 3n, it's a very simple problem because constraints define everything. So we should not solve differential equation from second law of Newton. So because constraints define everything. So let's consider the second case, k larger than 3n. So we call that system is overflowed, that we cannot satisfy some particular constraints and only partial we can satisfy constraint. So in a final case, k less than 3n, in that case, so we can solve our problem, and that problem is our goal. So how we can define constraint force? So the idea is similar which we considered before. So our total constraint force which acts on an ith particle is just a superposition of partial constraint forces which is represented as a gradient multiplied by some constant which we call Lagrangian multiplier. So in general, we have a system of equation. So first equation is the second law of Newton. So second equation is a definition of our constraint force, and third one is just our constraint, mathematical formulation of our constraint. So in general, so how many equations do we have? So we have a 3n equation from a second law of Newton. So we have a k equation from a constraint here. So in general, we have a 3n plus k equations. And how many variables we have to define? So we have to define 3n variables. So we have a 3n Cartesian coordinates, and we have we have k number of Lagrangian multiplier. So in general, we have to, in a sum, we have a 3n plus k variable. So the number of equations in the number of variables are concise. So that is a well-defined problem, and that problem can be solved. So in that problem, we have to define during our solution Lagrangian multiplier. So on the next lecture, we will discuss Lagrangian equation of second time, and we start our discussion with the generalized coordinates.